Okay. I think we should be live. Let me check this. Just give me a second. And also let me. Um, okay, just 1 second. I need to set up my voice agent. Yeah. Okay, now it should work. 1 second. This looks good. Okay. Yeah. Okay. Hey, can you hear me? Can you hear me?
Hi there. Lovely to hear from you. What's on your mind today?
Can you please have a look at my codex window and take a screenshot?
Take your time. If you're figuring out what to ask, you can just describe the task, paste text, or say what you're trying to do.
Yeah,
I can help with
have a
explanation.
look at my codex window that's open and take a screenshot. What the fuck? Okay, is my internet that bad? The live stream is working fine. Or not. What's my. Let me check what my speed is. Okay, I'm not even connecting to the servers. Oh man. Okay, yeah, my internet connection is really, really, really bad. I currently have the VM World Cup going on. I guess. Okay, 7 Mbit download is. Yeah. It's not fast, but it should be enough for us. Upload 3 MB, 4, 5. 5 is also not too bad for like just speech upload. Let's try again. Oh man. If this could work, please. So let's try again. Oh, that's already taking too long. Why the heck is it that slow? Hey, can you hear me?
Yes, I can hear you clearly. If you're testing your mic, it sounds good on my end.
Can you please have a look at the codecs window that I have open and take a screenshot of it?
Okay, I'll check for the codecs window and grab a screenshot for us. I don't see a window labeled codecs in the list. There's a Devon notebook, a browser tab, OBS, Finder, and a couple others. Which one is the codecs window? If it's the No problem. I'll grab the ChatGPT window and then describe what's visible. Looks like that window isn't available anymore. Let me quickly check what's currently open. I've captured the ChatGPT window successfully. From what's visible, you have a workspace on the left with items like Create Concept Notebooks and several project or task.
Concepts and go over the notebooks and have you to like explain concepts to me or like basically be my training or sparring partner. Um, so I can build an intuition and understanding for these concepts.
Love that plan. I can be your training partner for this. We can go notebook by notebook and concept by concept. First, we'll pick a specific notebook or section. Then I'll explain the idea in plain language, connect it to what it's for, and point out any common pitfalls. After that, I'll ask a quick check question to see if it clicked, and we'll move on at your pace. If you want, start by telling me the first notebook or concept you'd like to tackle.
Okay, please have a look at the notebook I'm going through now.
Okay, let me check the notebook you're on so we can walk through it together. I can see the 00A Vectors Embedding Softmax notebook. The TALPSO lays out a learning contract. It's about boundaries between tokenization, embeddings, logits, softmax, and how text gets selected and displayed, plus how to read changes without recomputing the whole model. There's also a route through the notebook section that suggests a sequence: tokenizer and decoding, then inspecting tokens, moving vectors into a 2D embedding view, comparing state and logits, and finally changing temperature and decoding behavior. For a clean start, and begin at 1, load the shared teaching model. Then we can step through each concept one at a time. Quick check. Do you want to start with embeddings and what they represent, or with logits and softmax and how they turn into probabilities?
Yeah, let's just go through the notebook step by step. I think tokenizer I got to basically split up the text in like as small chunks or tokens basically, um, but try to keep them like as recurring tokens. For example, like keep the vocabulary also not too large for efficiency or like training wise. Um, but yeah, use transfer the or put like turn the text into tokens. These tokens are then get into like vectors or like embeddings, and that step I would like to create a better understanding for.
Great. Let's build that intuition step by step from tokens into embeddings. Yes, perfect place to focus. An embedding is basically the model's way of giving each token a rich numeric identity. Instead of a token being just an index like token number 5, the model looks up a vector, a list of numbers that places.
Find tokens or like basically positions in like the latent space, I guess you call it, right? Um, and what I'm looking here then, like what is the purpose of the update delta y delta x? Um, is this somehow to visualize how like training or like going through different layers affects like the like what
Good question. Let's unpack what those updates are showing and how they relate to learning. Exactly. Embeddings place tokens in a latent space. Those update terms, like delta X and delta Y, are showing change. Delta just means difference. So delta X is how a vector changes in one dimension, and delta Y is change in another. In this context, it's usually illustrating how representations move when you apply a transformation, like a layer update, a change temperature, or a different decoding choice. It's not training itself, but a visualization of how the internal state or scores shift. So the big idea is you start with an embedding for a token, then the model applies operations that nudge that vector around. Seeing how it moves helps you build intuition for what each step does. Do you want to focus next on how logits and softmax relate to those shifts?
Based on feed forward also like a combination of tokens also moves like a specific path or like way in a latent space that we, then we can say like applying tokens or like applying transformations through the layers is basically all reduced kind of to like navigating just in the space to represent like a different state.
Yes, that's a really good intuition. You can think of the model as navigating in a high dimensional space. Each token starts as a point, an embedding, and then each layer applies transformations that move that point or the full state along the path. One nuance, it's not really combining tokens into a new single token in the embedding sense. It's combining information across tokens to update the hidden state, like attention mixing context, then feed forward layers reshaping it. The state represents the model's current understanding of what's going on, and after each step, the position changes, meaning the representation changes. Then logits and softmax read that state and turn it into scores and probabilities for the next token. If you want, we can look at a specific cell or visualization and interpret exactly what's moving and why.
Okay, so I think I got that now. And this then also like um, affects like the dot product, basically the new state it's in, right? And this turned then into the token probabilities with the softmax and their temperature or like the decoding settings then apply like top K and all these things, right? These are like not the model, but like additional added randomness basically on top. Okay, so and like the output of the model is basically are the dot products, the logics, right? Um, and these change based on a state. So are these like deterministic? Like, can I say when I input the same state or always the same like vector into the model, I get like the same output? Um, or like how does it make sense that okay, I have like a token that I turn into a vector and then I can apply some transformation for it and basically like or like apply like an additional vector, do like matrix multiplication and then therefore move in the latent space or like in the space in the multidimensional space. Um, and this allows me to do what or like this state is fed into the model at what point in the architecture.
Yes, the logits come from a dot product, or a very similar readout, applied to the model's current hidden state. And if the state and weights are the same, that mapping is deterministic. Same input state, same logits. The move and latent space intuition is right. Each layer applies transformations, like attention mixing context and feed forward reshaping. Those are matrix multiplications plus nonlinearities, and they update the hidden state. That state is what flows through the architecture. First, the token embedding, then positional information, then repeated blocks of attention and feed-forward updates. At the end, a final layer norm and the output projection produce logits, which softmax turns into probabilities. So you can think update, 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 then readout. That readout is where the model decides what token is likely next.
Okay, and what we describe the logits, and so we basically feed into the model a a a vector or like a specific state. We can say is this state like basically the point in latent space then, and then this applies some transformations or like multiplicates or does vector multiplication throughout the different layers or like applies transformations, and then what we get out is like are the logits, the dot products, like a value for every token we have. And then applying softmax gives us basically the probabilities where we can then apply additional mechanisms like temperature, whatever, on.
Yes, that's a solid description. The hidden state is like a point, or really a vector, in a high dimensional space. Each layer transforms it, mixing context and reshaping it, and the final transformed state is fed into an output projection. That projection produces logits, one score per vocabulary token, which are deterministic given the same state and weights. Softmax then turns those scores into probabilities. Temperature and decoding strategies, like sampling or greedy selection, come after that and decide how to pick the next token from those probabilities.
And
So, in
basically, if we have like words in latent space, but we could also have like sentences or like longer segments, right? That basically having like some longer segments lets us just navigate in latent space to like a more detailed point or like more detailed state or idea of state we want, right? But basically, it's the same here that we it's like a longer input or longer sentence, but we still feed in like only a specific state in the latent space kinda. So that doesn't change if that makes sense.
let's pin down that idea of state and how it behaves over a whole sentence. Yes, that makes sense with one small clarification. You don't keep a single fixed state for the whole sentence. Instead, the model carries a hidden state that changes at each position. Each new token updates the state based on the previous context. So you're still navigating in latent space, but the point moves as you read more tokens. At any step, the model uses the current state to produce logits for the next token. So it's not one state for the entire sentence, it's a sequence of evolving states.
This
Each
I have one word, okay? Then I add another, and then like a third and fourth, and I get even longer. And these are basically additional vectors. Then I have to like my initial word vector only. So let's say they just let me navigate in latent space more granular or like more with more control, or to like more detailed positions if that makes sense. But what still gets fed into the model is like that single state. Like I still feed in like a state. It's then like at a different position. Yeah, fine. And I can navigate with like longer prompts then better, let's say, or get like more my achieve or wanted behavior out. Um, because I can navigate, as I said, more detail to my idea or wanted state in the latent space, and that specific state then gets us always the same output.
Yes, that's a good way to think about it. A longer prompt shapes the hidden state more, so you can steer the model toward a more specific internal representation of what you want. But it's not a single fixed state forever. There's one state at each step, and it evolves as tokens are processed. At any given step, the model uses the current state to produce logits, and those logits are deterministic if the state and weights are the same.
Forward or like
One more
additional
nuance.
updates with every new token, but I mean, what's not like independent of the length, we always take then like this final point the we basically navigated to, or like this final point of state in latent space kinda, and feed that in. And this is then just a different position. That this updates with every new token, with every feed forward, or also with every layer we go through. Yeah, yeah, totally got that.
Yes, exactly. At each step, there's a current state, and that state is what gets fed into the output head to produce logits. The whole sequence length just determines how that state evolved. And yes, if you end up with the same final state and the same model weights, you'll get the same logits. So your intuition is right. You're navigating to a position in latent space, and the output is a deterministic readout from that position.
So it's basically like a geometry problem, and we could say that also like that the same prompts in different models with as long as they have like similar embeddings should like produce similar geometries or like forms in a latent space or paths kinda. Does that also make sense?
Interesting angle. Let me think about how geometry carries across different models. That's a lovely way to see it. And yes, part of it is geometry. But there's a key catch. Different models don't share the same coordinate system. Even if they behave similarly, their embedding spaces can be rotated, stretched, or organized differently. So the path in one model won't line up directly with the path in another. What can be similar is the function. Both may learn to represent meaning and context in useful ways. But the shapes you'd see in latent space aren't guaranteed to match.
Okay, so we are also with like neural network, what we're basically doing, our inputs are basically different states that represent semantic content or um, different expressions or like we are able to navigate with language to different states in the latent space, and this specific state then correlates to like a specific logic output, right? That's deterministic. So as long as we are able to like navigate to like the same state, exact same position, we will always get the same output. And close enough clusters, I would guess, also like pretty confident, like deterministic wise from the model. Um, is that right so far?
Yes, that's right so far. Language guides the model into a hidden state that reflects context and meaning. And from that state, the output head produces logits. If the state and weights are exactly the same, the logits are deterministic. For nearby states or clusters, you often get similar outputs, but it's not guaranteed. Small differences can still flip the ranking of tokens. So the geometry intuition is very useful, just with that bit of fuzziness near decision boundaries.
Okay, so I think we can continue in the notebook, right?
Nice. Let's keep going in the notebook and connect the next steps to what you already understand. Yep, we can continue. Since you've got the big picture, the next
Right, a 2D PCA view, which basically tries to show us that like with like what I said with semantic meaning, like things like circle, square, cluster, Z happy as emotions, cluster, red, blue as colors. What like an embedding model does, that it assigns vectors basically to like then understand meaning and based on that cluster or like position tokens in the space.
nice observation. Let's talk about what that 2D view really captures. Yes, that's the idea.
Sorry, I interrupted you, but I think my intuition was right, right? So let's go to the next step, contextual residual through additive updates. So let's look at that graph. Um, Regarding the angle from start, I guess like the first layer had the biggest impact on like move then for like direction in the latent space, and further changes like just followed that angle or that direction, like there wasn't like a big difference in angle changes. And block update norm, you might have to explain to me, please.
Okay, let's unpack what those angles and update norms are telling you about the residual updates. Your intuition is really good here. Angle from start is basically asking how much has the direction of the hidden state changed compared to where it began.
This basically is like we had just before what I can imagine. We have like a state, a specific vector that leads to like a specific position. That's our state in the latent space. And what we then do through the layers, apply some transformations. So basically like a path. I add like a short additional vector that leads to a different position. Then we have the next transformation, the next layer. Again, I can imagine this like a third arrow or like vector then being added to the path, kind of, right?
Yes, that's a great mental picture. You have a current state, a vector, and each layer adds a small update, like a little arrow, which shifts you to a new point in that space. String those updates together and you get a path. The angle from start tells you how the overall direction has rotated compared to the beginning. The block update norm tells you how big each step is, basically the size of that little arrow. Bigger norm, bigger move. Smaller norm, a gentle nudge. Together, they show how the model changes meaning over layers.
Nice. I think then this notebook is also almost done. Let's look at the last thing. And logits, like, should I know anything about logits? It's basically just the output, like at the final layer of the model, right? And that's the numbers are basically the outputs for it, right? Sorry, I think we're at the end of the notebook, right? Just one thing about logits. Logits are basically like any, like, basically just scores. Is there like a range to them? I don't know. Basically scores the model outputs at like its final layer per neuron, right? That can be mapped to token IDs then, I guess. Like every neuron has its own token assigned, or like also how does the sign work here?
Yes, the output layer produces one logit per token in the vocabulary. You can think of it like a score for each token ID. It's not literally one neuron permanently assigned to a token in a physical sense, but functionally it acts that way. The final projection maps the hidden state into a vector of scores over the vocabulary. The highest score is the most preferred next token before softmax and decoding. So, yes, each logic corresponds to a token ID, and together they form the model's belief about what should come next.
I'm sorry, I didn't listen properly. There is a range to it, or basically it gives us for our whole vocabulary. The output is like for our whole vocabulary for each item a number, right? And that's ranged, or like we turn this into probabilities with softmax. Then I also get that. But how do the numbers outputs for like the how does this work?
Good question. Let's zoom in on what those numbers actually are and how they're produced. Right. Those numbers are the logits, one for every token in the vocabulary. There's no fixed range. They can be big or small, positive or negative. The model just outputs a score for each token. They come from a final linear layer, sometimes called the output projection or readout. It multiplies the hidden state by a weight matrix and adds a bias to produce a score for each token. That's why it's deterministic. Same hidden state and weights, same scores. Then, softmax takes those scores and turns them into probabilities across the whole vocabulary.
Okay, so I think I got everything in here. Let's go to the next notebook. That's this one. Please have a look.
Got it. I'll pull up that notebook and then we can dive in from the top. I can see the Double O Transformer State Notebook, and it looks like this one is about how a decoder model carries and transforms state across blocks, then turns the state at a position into a next token distribution. A key idea in the learning contract is the sequence as a table, with one vector per token position, not a single sentence vector. Each block updates the state, and the final position state becomes the logits for the next token. If you want, we can go step by step.
Basically what we just had, right? So I'm just going through the notebook. So far, nothing looks new to me. Here we have tokens assigned to different positions in the sentence or input and the decoded strings. Token ribbon, yeah, also nothing new. Um, let's look at this maybe.
Yep, that tracks. A lot of this is reinforcing what you already built. Token IDs at positions, decoding back to text, and a ribbon or table showing the per position state. That's all familiar groundwork. If you want, we can jump to the first spot that adds something new. Usually it's where they separate the token state from the model state, or where they show a control that changes the depth and lets you see how the state evolves. If you scroll to a section about state per position, depth, or trajectory, tell me what you see, and I'll help interpret the new visualization or metrics.
Okay, here's a new view. Please have a look.
All right, let me take a look at that new view and think through what it's showing. I can see the new view. It looks like a grid of angles with depth or checkpoint on the vertical axis and token position on the horizontal axis, plus a color bar showing the angle in degrees. The title suggests it's the direction turn caused by the latest complete block. So each cell is showing how much the newest block changed the direction of the state at that token position. Brighter or warmer colors mean a bigger turn, darker colors mean a smaller turn. If you adjust the checkpoint or position controls, you should see how different layers or positions get bigger or smaller updates. That helps you spot which parts of the sequence are being strongly revised by the latest block.
Sorry, explain the last part again. Revised. Like we have like the state that we just discussed, and that's fed into like the different blocks here. And the color highlights the like logit for basically every token, and the higher the lighter. That's right, right? And then we see like in the rows the different states, and at the last state, um, how do I know now what token will be the chosen one with the highest logit?
Sure, let's clarify what the colors mean and how you'd actually pick a token from this. Not quite. In this view, the colors are showing the angle change, the turn in direction caused by the latest block, not logits. So each row is a checkpoint or depth, each column is a token position, and the color is how much that block rotated the state there. Warm colors mean a bigger change in direction. Dark means small or none. To know which token would be chosen, you don't read this plot. You need the final hidden state at the current position. Pass it through the output projection to get logits for every vocabulary token, then either take the highest logit, which is greedy, or sample after softmax. So this heat map tells you where the model is revising its internal representation, not which token wins.
Okay, so what does this mean here now?
This view is basically a diagnostic for where is the model changing its mind. Each cell says, at this layer and this token position, how much did the newest block rotate the state vector? Big rotation means that position's representation got a strong update. Small rotation means it was left mostly as is. So it's not directly about choosing a token. It's about
Like in big angle change, or can it be also like just a continuation in the path, like really a straight vector, and basically in line with like the reverse vector, so to say, um, this would also kind of also like a change.
Nice nuance to dig into. Let me think about how to separate rotation from other kinds of change. Great question. In this plot, rotation really means a change in direction, so a big angle between the previous state vector and the updated one. If the new vector points almost in the same direction as before, that's a small angle, so it shows up as a small rotation. It could still change in size, meaning the magnitude, while staying in that direction. This angle view doesn't focus on that.
Okay,
It's
but
mostly about direction changes. So,
what does the
yes,
difference with like direction and length mean? So, no, sorry, confused. Both say direction. So in L2 we basically measure distance and length, and the last layers here have the most impact on like direction, I would say, right? So affect the output the most. So we couldn't say like we get the same output after layer 10. It would be like completely different. And for what does cosine distance mean, the measure then? Try again.
sure. Cosine distance is just a way to measure how different two directions are. If two vectors point the same way, the cosine similarity is close to 1, and the distance is close to 0. If they point in very different directions, the distance is larger. It ignores length and focuses on orientation only. And yes, later layers often have a strong influence, but you can't assume they always dominate or that anything after layer 10 is completely different. It depends on the model and the input. Earlier layers set a structure, and later layers refine it. The final output comes from the last state, and it is deterministic given that state and the weights.
Is this basically what like trajectory has two axes means? Like just continuing a vector or like changing angle?
Yes, that's the idea. When they talk about a trajectory with two axes, it usually means you can think of two kinds of change. One is continuing along the same direction, like extending the vector. The other is changing direction, like rotating it. Cosine similarity or distance captures the rotation part, the angle. A norm or magnitude captures the length, how
That's
big the
the
state or
confused thing I have open here. And um, this is basically showing us how like basically what you said, that you can change direction by like token path, by adding more tokens, or like depth path by going through the layers. Is that what this is trying to tell us?
Okay, let's take a moment to interpret what this view is really comparing. Yes, that's the idea. This view is comparing two ways of moving through the same underlying state grid. One path keeps the token position fixed and moves through depth, meaning layers. That's the vertical line. The other path keeps the checkpoint fixed and moves across token positions.
Okay,
That's the
so this is
horizontal line.
basically
They meet at the same
this is
endpoint.
basically the same, but just showing us this as a path. So basically, each transformation is added up from the initial starting point. Is that right? Where we can see that like the token path with adding tokens or like expanding the input gives or changes the position more than like the depth or like going through the layers with like a fixed prompt basically, since it's layer after layer with the same prompt or like from the same input. This doesn't then have that much effect on like positioning. Is that understanding or interpretation of this right?
Nice. Let's walk through what that path view is actually saying about token moves versus layer moves. Mostly right, with one small caution. That path view is showing how the state changes as you move along two axes, across tokens, which is the token path, and through layers, which is the depth path. Each step adds a transformation. So, yes, it's like building a trail from the initial point. But it's not always true that adding tokens moves more than going through layers. It depends on the model and the context. Sometimes layers make large directional changes, and sometimes adding tokens reshapes the state more. The key is that both paths are two different ways of slicing the same grid of states, and they meet at the same final point.
Okay, now let's look at this next visualization where we have basically different prompts fed in. Some for what is multiplication, what is like subtraction, different prompts here, right? And this shows us then also with like, I guess, token per token from the initial token, like what, and then each token added, um, how they evolved like in the space with like the final states being the S14 points. Also, is that interpretation right so far?
Okay, let's think through what this comparison is showing, especially how those prompts evolve token by token. Yes, that's a good read. It looks like a comparison of different prompts, each token by token, and how their states move through the model. You can think of each prompt as producing a path across positions, and at each position, the state is updated as it goes through layers. The final states you mentioned, like those S14 points, are the model's last states for each token position, meaning after the full depth. So you're seeing how different prompts trace different trajectories. Some may diverge early, some stay similar for a while, then split. That helps you see where meaning and context start to differ in the model's internal representation.
Okay, I scrolled a little down, a little further. So what does this do corresponding blocks at similar direction mean? What are like corresponding blocks in that sense?
Interesting point to dig into. Let me think about what corresponding blocks really means here. Corresponding blocks usually means blocks at the same depth in the network, like block 3. Okay, let me take a look at that section and think through how to explain it clearly. Nice. I can see that section. It's comparing how similar the updates are between two different prompts, block by block. Corresponding blocks means the same layer index in each run, like block 3 in one prompt compared to block 3 in another. The metric is the angle between the update directions those blocks produce. Smaller angles mean the blocks push in similar directions. It doesn't prove they do the same computation, but it suggests that the model is using a similar kind of update at that depth for both prompts.
And could we say that, or could we like conclude that because I see here a same operator mean, um, that we could say, okay, maybe by like detecting different angles or like changes a state underwent kind of through the layers, and then say, okay, now the model really deterministically, like we can be assured that it now did like subtraction or like whatever. Oh fuck. Okay, so I was thinking we see that like same operation mean is like a clearly different like transformation across the layers basically than the others. Neither mean or same answer mean are kind of the same. And the same answer mean I think is anyways like not But I was thinking, since same operator mean shows like a clear difference here to like neither mean, could we say by looking at the transformations through layers that, well, now we can like be deterministically sure that something um, applied this principle or like this specific transformation to the text? Like or it's like in that domain of knowledge if we like see that transformation to happen through the layers.
It's more of a strong hint than a proof. If corresponding blocks
Continue, please. Continue, please.
using the exact same rule or principle. These measurements are observational. They show similarity in direction or size of updates, not the underlying computation. To claim a specific rule, you'd need deeper analysis or a more controlled experiment.
Okay, and what I'm looking at now, and the last section is, so section 8 is, the model def is fixed, the slider changes the diagnostic checkpoint. The liquid model was designed and trained with 14 blocks, 8 convolution blocks, and 6 attention blocks. These are basically the layers we are talking about the whole time, right? And what this is now doing, take a screenshot please, is say, okay, if we cut off after a specific layer called checkpoint here, I would guess, we then of course get like a different output. Take a screenshot again please and continue.
Yes, I can see it. The slider is choosing a diagnostic checkpoint inside a fixed architecture. The model still has the same total depth, with those convolution blocks and attention blocks. But you're effectively asking, what if I stop here and read out the state now? When you do that, you take the current hidden state, apply the final normalization and the output head, and you get logits and probabilities for the next token. So, yes, if you cut off earlier, you often get a different output because the later blocks haven't refined the state yet. It's a bit like pausing a thought mid process versus letting it finish. Same rain, same rules, just a different point along the path.
Okay, I think I got that as well. Now, yeah, I think I take